Welcome back to another exciting chemistry lesson. In this lesson, we are going to look at the periodic table to determine if an atom is going to gain, lose, or share their valence electron to be least reactive, or better term, to be stable. Now, most elements on the periodic table are too reactive, okay? That is, they have to make a chemical bond with themselves, or they have to make a chemical bond with other atoms to be stable or to be least reactive. Now, let's look at this. If we look at the periodic table and we learn that there is one particular group that's considered to be stable, and this particular group is known as group 8A. Now, this group has a special name. It's called the noble gas. So if we go back over here, so group 8A, they are not reactive at all, and they have a specific term for it. The term is inert. Now, another better term is noble gas. Think of the term noble. If you are noble, you're pretty much stable, right? So what's so special about being noble? And now, the better question would be like, what do elements or atoms that are not noble would like to be? Of course, they want to be noble. So in this case, all the atoms on the periodic table that are not noble, they would like to have that nobility. And how are they going to do it? That is by gaining, losing, or sharing their valence electron. So here, this is where we go back to our electron configuration. What's so special about group 8A? Well, they have their outermost shell, okay? They have a full outermost energy level. That is, the whole entire level, at the highest energy level, it has all the possible orbitals filled with electron. And we remember that the S and the P is where we find our valence electron. And we know there are 2 S possible, and there are 6 P possible. 1, 2, okay? And P is 1, 2, 3, 4, 5, 6. What's 2 plus 6? 8. And we also learned that the group number right here also equal to the number of valence electron. So what you notice right here, they have 8 valence electron, except for helium's only has 2 valence electron. So helium is an exception, okay? So a better term of putting this is like this. If we look at any elements on the periodic table, and this trend usually applies to the group A's, which are the representative elements. Group 1A has 1 valence electron. Group 2A has 2 valence electron, okay? Group 3A has 3 valence electron. And 4 has 4, 5, 6, 7, and 8, okay? So that's how the pattern for the representative elements work. So let's look at this. If you are on the periodic table, there's 2 directions. You are going to have to be noble. To be one of the noble, you can be going forward to be the next noble, or going to go backward to look like the previous noble gas. So let's look at an example of fluorine atoms right here. You have 2 options. You can gain electron, which allow you to have an electron configuration of neon, right? So to do that, how many electrons do you need? You need 1 more. So here's the other option. The other option is you are going to lose all of this 7. How do I know it's 7? Because in group 7A, I have to lose all the 7 valence electron so that I look like the previous noble gas. So which one is easier? Well, it's common sense to us and to atom in nature as well. It is easier to gain 1 more electron. And that's the reason why all the elements over here have a high tendency or electronegativity, that's the term, that they want to gain additional electron to have the same electron configuration as the noble gas. So what did we learn? If we look at this, look at number 8. What is 8 divided by 2? That is 4. So 4 is right in the center, okay? So keep that in mind. We are going to cover that last. But anything from 5 to 7 or 5 through 7, we would have gain, okay? They need to gain as much as they need to be like one of the noble gas. So the key is to gain electron to have the same electron configuration as the noble gas. For nitrogen, how many more do I need? 1, 2, 3. For oxygen, how many more do I need? So I'm going to put plus plus 3 electron here, okay? For oxygen, how many more do I need? Well, for any element in group 6A, how many more do I need? 1, 2. So this will be plus 2 electron. And then group 7A, we learned that it's going to be plus 1 electron. So that is the general pattern behind it. Now, what if it's less than 4? So in this case, we have 3, 2, 1. So in this case, instead of going forward and gaining electron, we will lose the outermost shell and become one of the previous noble gas. That's the better way to do it, okay? So if I look at this, let's look at all the elements in group 1A. So let's look at lithium. In this case, the lithium atom right here has 1 valence electron because 1 valence electron right here because it's group 1A. So therefore, it's going to gain 7 more just to look like neon. That's too much. So we had to go backwards. It's going to completely lose the 1 electron in its outermost shell completely. So in this case, look at lithium. If lithium is right here, right, we have the first 2 electron here. And then we have the 1 electron, the lonely 1 electron there. So what's happening is this energy level, it needs 7 more. That's too much. So what it's going to do is this is going to lose. And look what happened. Now you have a full outermost shell by taking away the outermost shell that they had before. So that's a strategy for metals. The same thing for beryllium. It has 2 electrons on the outer shell. It's too much to gain 6, so it's going to lose 2 valence electrons. So that way that whole entire shell or energy level is completely gone. So now the inner complete shell is now become the outermost shell, and that's very challenging to understand, okay? So basic metal, they lose that valence electron. In the process, they also lose the energy level as well. So now the next outermost shell will become the outermost shell. So that's the next outermost energy level will now become the outermost energy level. And that's the logic behind metals losing their valence electron to be stable. So let's look at group 1A. How many do they need to lose? So in this case, they need to lose 1 valence electron, okay, which completely get rid of their whole entire shell. In this case, for metal, what do they need to do? They need to lose 2 valence electron, okay? So I'm going to change this to blue. So I want to underline this blue, okay? And then for group 3A, they would need to lose 3 valence electron. And over here is gain. So keep that in mind, okay? So this trend is applicable for group 1A all the way through 7A. But as you can see, the metals in group B also have similar function, but it's pretty difficult to predict how many electrons they are going to lose. That's why we look at group 1A all the way to 7A. So let's look at an example. In this case, we have the same statement. To be least reactive atom, gain, blank, lose, or share their valence electron to have an electron configuration of the nearest noble gas, okay, which has the full outermost shell. In this case, we look at this electron configuration. We know 1s2, 2s2, 2p6, 3s2, and 3p1. This is the last part. 3p1, where is it? Well, that's S. P1's right here. So 3 going across P1, that's aluminum. So we figured out that is aluminum right there. It has how many valence electron? Well, 2 from here, 1 from there. That's 3. Isn't that nice? You don't even have to look at the periodic table. You just have to look for the periodic table because we need to know what is the name of that atom. Now, if it has 3 electrons, of course, it's going to do what? We mentioned right here, all the elements in group 3A will lose 3 valence electron. Okay, so they will lose how many? 3 electron total. So now that outermost shell is completely gone. So you would have a full outermost shell, which it used to be the next inner shell, right? So that's the key, which look like what? If I lose all my electron here, now I go back here, what do I look like? I look like neon, which is one of the noble gas. And that's the beauty aspect behind that. So it's given to us on the periodic table. Now let's look at another one. In this case, we have the same statement, right? Atom would lose or gain or share the valence electron to be stable in order to have that electron configuration of the nearest noble gas. So in this case, we have 1s2, 2p5. So that's 5 to be up there. So what's the total? In this case, 2 is the highest energy level. 2 plus 5 is 7, okay? But how do I know it's fluorine? Well, I go to the last part, 2p5. I go up here, 2p5. So 2 going across, p5. 1, 2, 3, 4, 5. That's fluorine right there. See? Easy, isn't it? So now it would gain, of course, it would gain because it has 7. How many more does it need? It only needs 1 more electron. And this is given to us on the periodic table right here. You see how that works? Given to us on the periodic table. 1 more to look like neon. And there you go. Isn't that nice? So the better term in this case, if we look at this, fluorine gain 1 more. So this is going to be neon, not argon. Okay? And that's the reason behind it. Now let's look at the last part of the puzzle, is what happens when if an atom is right in the center at 4 valence electron. Well, one is gaining, one is losing. The middle part is gonna be sharing. So in this case, atoms like carbon, okay, atom in 4A, carbon, silicon, and germanium, all those atoms are more likely to share the valence electron. So now they are sharing. So therefore, the number of valence electrons is going to be count for both atoms. So now both of them are stable, or whichever atom involved in the sharing process are now stable. So you have heard the phrase, sharing is caring. And this has happened in nature as well. It is so effective in terms of sharing electron that we have the whole entire chemistry dedicated to understanding atoms sharing electron, and that is organic chemistry. Organic chemistry is talking about chemistry that dealing with chemicals that has carbon in it, which involve atoms sharing their valence electron. So that is how we look at the periodic table to determine if an atom is gaining an electron or losing the valence electron, or even sharing the valence electron, to be least reactive by having the same electron configuration of the nearby noble gas. And we'll see you next time on another exciting chemistry lesson.